All right, so we're going to talk about numerical solutions. So we're going to do two kinds of numerical solutions in this class. I'm going to have you solve a finite difference solution to show you how numerical solutions are done, and it's really, really easy. It's something you can do in a spreadsheet. And then we're also going to be using phase 2 in rock science, which is a finite element program, to do flow. Doing flow with finite element programs is easy because doing flow is really simple. The boundary conditions are simple. The model's simple. It's probably the one kind of finite element analysis that anybody can do. You don't have to worry too much. Doing stress, strain, and soil interaction problems with finite element, that's really hard. It's easy to make mistakes. If you don't do a good solution, it's bad. But flow is really easy, so it's a really good tool to use. And we're going to turn you loose on doing flow in 2 dimensions with finite elements, almost to the black box without you even having to know anything about finite elements. But we're going to start with a finite difference solution, because I think it does a really good job of showing you what approximations we make and how we do numerical solutions. So we're going to be doing a finite difference solution. So we're going to be using a Taylor series expansion. So I'm sure you all remember Taylor series. And if you don't, I'm sure you're going to remember them in about 10 minutes. And then we're going to solve a simple confined flow boundary condition using that Taylor series expansion and the finite difference one. I'm not going to talk about filters during the lesson, but there's a whole section of filters in the book, and that is one of the learning objectives, to know how to design filters. It's pretty simple stuff, so make sure you're going over that. And then finally, we're going to model 2D, both confined and unconfined flow using finite elements. That's what I was just talking about. So this one, I'll make a big point here. This one, you got to read that material in the text, and I'll give you a homework problem on that. But I think it's really, really simple. So if you got questions about it, bring them up in class. All right, we're going to do Taylor series expansion. Now, I'm sure you remember this. It's just been a while. If I know the value of some function, I have some function here of x. I got some f of x. And if I know that value of an x, I can approximate the value at some place at x plus delta x by this equation. So if I want to know what's going on here at x plus delta x, so this is delta x. Well, I'm going to start with the value at x. Right? I'm going to start with this value. And then what I'm going to do? Well, I'm going to differentiate f of x with respect to x. What's that? That's just the slope of the function, right? Let me get rid of this thing. So that's the slope of the function times delta x. Well, that's pretty simple. All that is, I'm going to take the slope of this function let me move my delta x out here a little farther so I got room to make mistakes. Let's say this is going to be delta x here. So my first approximation is I'm going to go delta x away. I'm going to take the slope and multiply by delta x. Well, that's going to give me that point. Well, that's a decent estimate, but it's not really great. So what am I going to do next? Well, I'm going to take 1 over 2 factorial times the second partial. What's the second partial of f with respect to x? That's the curvature. Right? And I'm going to add that to delta x squared. So that's going to give me some point down here, actually, is what it's going to do. And then I'm going to take the third partial, and I'm going to add that in 1 over 3 factorial times the third partial, and that's going to give me another one here. And if I keep doing that, I'm just going to zoom back and forth and zero around, and finally, eventually, I'm going to get really close to that point where it really is. That's the Taylor series expansion. Oh yeah, you're saying now, I remember. And I promise you, you did learn that at one time. Okay. So if I want to know f of x at minus delta x, I can do the same thing. I'm just going to plug minus delta x in there. Right? Page up. Sorry about that. I went faster there. Right? So I can do it frontwards, and I can do it backwards. One's called the forward difference, and one called the backward difference. Right. So you know what the Taylor series expansion is now, right? Okay, we're going to do this really cool trick. But I got to tell you, I got to do some notation. It's really hard to write f of x1 and f of xi and f of xi plus 1 and f of xi minus 1. So we're going to use some notation where f sub I means f of x at I, and f of x of I plus 1 is the f of x at I x plus 1, or the next delta x over. Right? You with me? So if I do that, then the forward difference is, my equation is just that f of I plus 1, which means that's f of x plus delta x, is just equal to the first partial evaluated at I times delta x plus 1 over 2 factorial of the second partial evaluated at I times delta x squared, et cetera, et cetera, et cetera. So I'm just changing notation so it's easier to write. Everybody with me? Okay. Then I can do the backward difference the same way in the other direction. Notice when I do the backward difference that I get these pluses and minuses because delta x is negative in that direction, and one time I'm squaring it, and one time I'm not. First it's just delta x times it. That's going to be negative. Then it's going to be squared. That's going to be positive, and then it's going to be cubed. That's going to be negative. So it's going to go positive, negative, positive, negative, positive, negative, which is really going to be helpful here in a second. So now when I subtract these two equations, and I'm going to throw everything away but the first two terms, because I'm an engineer. One term doesn't seem like enough. Two seems pretty good. After that, it sounds like work. Right? So if I throw everything away but the first two terms, this is the equation I have. I have f of x at f sub I plus 1 minus f sub I minus 1 is equal to 0, because these two guys cancel out, plus 2 times the first partial of f with respect to x times delta x, plus this error term on the end. So as long as the error term is small, things are good. So what's really nice about that is I can then approximate the first partial of f with respect to x as this. Right? I'm taking the error term, I'm going to throw the error term array, I'm going to solve for the first partial of f with respect to x at I, and it's just going to be equal to f at x plus delta x minus f at x minus delta x divided by 2 times delta x. Which you're saying, well, that's pretty stupid. I could have told you that a long time ago, because all I'm saying is that if I want to know the slope at this point, all I got to do is connect these two lines together and divide the change in height by 2 delta x, and it's equal to the slope at that point, right? But we proved it mathematically, which means it's right. Right? You understand that? That's all we're doing. It gets better, though. I love mathematicians. I can't figure out how they figure all this stuff out. It's like going to like a really beautiful concert, and the guys, and you're thinking, how did this guy dream up this music, and then that guy learned to play it? And that's just amazing. But I just want to listen to it. I don't want to do it. I just want to listen to it. That's why I'm an engineer and not a mathematician, right? Okay. So these are my two equations again. We're going to do something fancier yet again. Because before we subtracted those two equations, right? And we subtracted those two equations, and we got a very simple equation to approximate the slope of the line at f of x, right? So now we're going to add these two equations, and we're going to keep only the first two terms. Now we're going to add them, right? And so that's going to give me f of I plus 1 plus f of I minus 1. I'm going to get 2 f of i's in there. Now notice that every other term is going to go away here, right? So this term goes away, and this term goes away. I'm only going to be left with the even number terms on this baby because they're negatives. And so now, look at this. So I got this little error term there. Look at this little baby in there I got. What is that? That's the second partial of f with respect to x. Now, why would we want to know the second partial of f with respect to x today? Well, what's the Laplace's equation? The second partial of h with respect to x plus the second partial of a with respect to where are we going with this? We're going to use this to solve Laplace's equation. So, I'm just going to solve for the second partial here. Now I have the second partial of this function with respect to x, and if you look at this carefully, it's going to be the value at f of x plus delta x minus 2 times the value at x plus the value at x minus delta x all over delta x squared. And now all I got to do is push that baby into Laplace's equation, and this is it, right? I just need to substitute in there for f the potential function. Oh, and I got to do it in 2 dimensions too. But doing it in 2 dimensions is easy. I just did it in 1 dimension because it was easier to talk about, but doing it in 2 dimensions. So now now I have a function that's g of x and y instead of just of x. And I'm going to start off at this point right here, which is xi, yj. I'm going to use the same notation, except I got i's and j's now. So this is gij. It's not gi joe, it's gij, which is the value of g at x and y. All right. And so if I look at these 4 nodes surrounding the point ij, this is I plus 1j, this is I minus 1j, this is ij plus 1, this is ij minus 1. You got the notation now? We're just incrementing, same notation except it's now in 2 dimensions. Okay, so I can expand that whole thing into 2 dimensions, and now that what I can say now is the second partial of that function with respect to x is going to be f of I plus 1. That's f at x plus delta x and y minus the value at f and y at the value of f at xy plus the value of f at x minus delta x and y divided by dx. And similarly, I can do it in the z direction. I said y, it should be z because we're doing this in x and z, right? I can do it in the z direction, and it's just the other. I just have to increment the other counter. Okay. So now all I got to do is this equation? Is this an easy equation? That's an easy equation. We can probably get high schoolers to calculate that, baby. So all I got to do is solve that equation for every node, and I've solved Laplace's equation, right? So all I'm going to do is I'm going to put these approximations for that partial in here, and this is all I need to solve. That's way easier than drawing lines. So if I let, I'm going to make it even easier because I'm going to say delta x is equal to delta z. That's nice because then what happens? These 2 values go away. And then if I know that kx and kz may not be equal, so I'm going to say, well, I'm going to have kx equal to some alpha for kz, so just some ratio. Then this is my solution. This is even easier. I don't even have to worry about the x's and z's. I just got to make sure that delta x and delta z are equal. And all I got to do is know the function. And what is our function at every node? What's that function that it's the value of what? The drive slow? Total head. The potential is total head. So all I need to know is the value of the total head at every point, and I can solve this equation. So if I solve for the value of f at the node that I'm interested in, f of ij, I'll find out. This is just algebra, but the value at f and I and j is equal to alpha times fi plus 1j plus alpha times fi minus 1j plus f of ij plus 1 plus f of ji plus 1 all divided by 2 plus alpha. That's nice. I'm going to let, for our first problem, we'll just let kx is equal to kz and then alpha is equal to 1, and this becomes really simple. So what does that actually say? Let's see, do I have a picture of this? So I'm interested in this node, right? I want to know the head at this node. What does this equation say? It says the head, the correct solution to the Laplace's equation is the head where I'm standing right now is the average of the head of the 4 guys next to me. That's pretty easy. I think I can do that. So we're going to solve that equation. So head, that's what we're interested in. Okay, so what we're going to do is we're going to do a finite difference solution. So we're going to break our flow problem up into a bunch of little squares. Now the way we solved this, we said delta x has to be equal to delta z. or it gets more complicated. So our squares have to be square. They can't be in the other direction. And then at every point here, I'm just going to put a node at every point, and all I have to do is pick a value of the head at every point so that it's equal to the average of the other ones. But I'm missing what part of my differential equation solution right now. To give you a big hint, that's the general solution. What have I not accounted for so far? No, well, I'm assuming k is equal. The two k's are equal. I can do this with the alpha in there, right? Every differential equation has a general solution and a specific solution. A specific solution, you take the general solution and you have to apply the boundary conditions, right? So I need to deal with the boundary conditions. But the equation for this node is just this average other one. So I can write that equation for every node, and I just have this huge system of linear equations, right? So all I need to do is, I got a huge matrix, I just got a huge matrix problem I got to solve. Wow, computers are good at that. But I got to apply the boundary conditions. So let's talk about boundary conditions. Well, the equipotential lines, h is constant, right? So if h is constant, then all I have to do for those lines is set the value of the solution to whatever it is, because the h is constant. That's easy. So right. So if I take this as if I take this as datum, and this is going to be h1, and this value is going to be h2. All I got to do is every one of these nodes, I just have to write down h2, 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 and over here I just have to write down h1. h1 is fixed. That's the boundary condition. The head's constant. That was an easy one. What's the other boundary condition we got to deal with, though? Flow lines, right? The other boundaries are flow lines. So that one's a little harder. Let's figure that one out. I had to use HH and HTail. Oh, well, sorry about that. Okay, well, the no-flow boundaries, that's the no-flow boundary. At the no-flow boundaries, at the flow lines, what we know is there's no flow perpendicular to that boundary. That's what it means. So that means in this case that the velocity in the z direction is going to be equal to 0. So the way I'm going to do that, how can I ensure that there's no flow in this direction? Well, the way I'm going to ensure there's no flow in this direction is I'm going to put a pseudo node on the other side of that boundary. I'm going to put them, I call them mirror nodes or image nodes. And then I'm going to write the equations to ensure that there's no gradient in this direction. And remember our first Taylor series expansion was that dH dz was equal to h1 plus hi plus 1 minus hi minus 1 divided by 2 delta z. Well, what's dH dz? That's the change of head in some direction, right? And if we're going to have no flow in that direction, there can't be any change in head in that direction. So all I have to do is set this thing equal to 0, right? So I'm going to set this thing equal to 0. And if I set this equal to 0, it just says that h at j plus 1 has to equal h at j minus 1. So all that says is this has to be equal to that, right? Which should make sense if the head's the same there and there, there's not any flow. So all I have to do is plug that back in my other equation. And my equation now is that for the value, let me do this. My equation for the value at ij is just the average of the other nodes, right? So that's just h at I plus 1j, h at I minus 1j. But this and this are equals, so it's just 2 times h of I j minus 1. So all I have to do is plug this equation in for all the nodes that are along this boundary, and I've satisfied that boundary condition that there's no flow perpendicular to that boundary. So this is really, really simple. So now I'm going to take our break, and we come back. I'm going to show you how to solve this in a spreadsheet, and it'll be so simple you'll be so ecstatic you won't want to eat or anything tonight. You just want to go home and drink beer or something. All right, so let's take 5 minutes and come back.